Alright, so yesterday we talked a little bit about forces and Newton's first law. I now want to formally give you guys Newton's first law and some notes on that and some practice problems. So Newton's first law says, this is from our textbook, an object at rest remains at rest, and an object in motion will maintain its motion with a constant velocity unless the object experiences a net external force. And we kind of emphasized that yesterday. It has to be a net external force. In your middle school, we always talked about a force acting on it. Well, sometimes an object will maintain its state of motion even though several forces are acting on it. They're just balanced forces, so we don't see a change in motion occur. So Newton's first law, another way we could say it is that it's a law of inertia. And inertia is the tendency of an object to maintain its state of motion. When you're driving in a car and you crash into something, you don't have your safety belt on, you go flying through the window because you, the object, wants to maintain its state of motion of going however fast the car was going. So that's what carries you through that window, is your inertia. So acceleration is determined, remember what an acceleration is, it's a change in velocity. That could be a change in direction or a change in speed, is determined by a net external force. What's a net external force? We say it's the total force resulting from a combination of external forces on an object, sometimes called the resultant force. So imagine, we talked a little bit about free body diagrams yesterday. We're going to add up all the forces acting on an object, and if there's an unbalanced force, that's what we're going to call our net external force. For instance, right here we have a car. You've got the force of gravity pulling it down. We have the force of the ground pushing it up. We'll learn later on we call that force of the ground the normal force. We have resistance. Now that resistance could be a sum of several resistance like friction, air resistance, those sorts of things acting on the car. And then we have the force of the ground pushing the car forward. As the car pushes against the ground, those tires push against the ground pushes back, and then that causes the car to go forward. Now it says the vector sum of all the forces acting on this car is 0. Notice that all these arrows are the same length and they're in the opposite direction. So if we let to the right be positive, the force forward is positive with that length. The force of friction is to the left, or that would be negative in this case, with that length. If you knew some numbers to these, one would be negative, one would be positive, but the magnitudes are equal in length. So when you add them, you get 0 net force going left or right. Same thing with the up and down directions. They add up, they cancel each other out. Now the question here is, does that mean the car is sitting still? So the acceleration is 0 because all the forces cancel out. Does that mean the car is sitting still? Well, no, it doesn't. It just means it's maintaining its velocity. So if the velocity is 0, it's maintaining a 0 velocity. If you've got the cruise control on and you're going 60 miles per hour, that means that you just stay at 60 miles per hour. So keep in mind, we don't need a net force to maintain a velocity. What we need is a net force to accelerate, to change the velocity. Force changes velocity. Now I want you to look at page 133 and try numbers 1 through 4. You can pause the video here if you want. These are the answers to those pages. And what I'm going to do is I'm going to work out each problem for you here in a minute, but I want you to try these problems first, and then if you need help with, say, number 3, you can skip the video along till I talk about number 3. Keep in mind that force is a vector, so you should have a direction on with most of these. Alright, so our next one here, it says a man is pulling on his dog with a force of 70 newtons directed at an angle of 30 degrees to the horizontal. Find the x and y components of this force. So I'm just going to start off just kind of getting you in the habit of drawing a free body diagram. I'm going to let that be the dog, and I'm just going to draw the vector here for the force acting on this dog. We're going to pretend like it's acting on the center of the object's mass right here. And so I'll let to the rightward force here be a red vector. That's the force in the x direction. And then the y directional force, I'll make it blue. And so all they're wanting to know is, what are the components of this force here? So this is a 70 Newton force. and this is at a 30-degree angle. This is just like when we did projectile motion, where we say, okay, here's the force in the x direction, here's the force in the y direction. In projectile motion, we call this VIX and this VIY. We're not talking about initial velocities here. We're talking about forces in the x and y directions. So we're going to use our Oscar had a heap of apples again. That's our sine, cosine, and tangent. So this is the sine of theta, cosine of theta. And I won't write this out every time, but it's just in case you're picking up in the middle here, you can understand what we're doing with the trig here. Now, let's suppose I want to know the y force first. This is the opposite side to this angle that we're talking about. This is the hypotenuse. Which trig function uses opposite and hypotenuse? It's going to be the sine. So I'm going to write out the sine of my angle, sine of 30, is equal to the opposite, Fy, force in the y direction, over the hypotenuse, 70. So 70 times the sine of 30 is equal to the force in the y direction. So make sure your calculator is in degree mode. I know a lot of you are taking a math class where you're doing radians. So just hit mode, and degree should be highlighted. Type in 70, sine of 30, and you should get 35. You could use special rights on this problem, but not all of them are going to be 30, 60, 90 triangles. So I know that the force in the y direction, it's an F, is going to be 35 newtons. Do the same thing for the x direction, except for this time you're going to use cosine because x direction is the adjacent side. So 70 times the cosine of 30 will give you the force in the x direction. So 70 cosine 30 gives me 60.6. So 60.6 newtons is your force in the x direction. Next one. Oops. Keep going on to the next slide. I need to add one here. There we go. So for the next one, once again, I'm going to draw a free body diagram. So pause the video. Try to draw a free body diagram with what's going on in number 2. So it says a crate is being pulled to the right with a force of 82 newtons to the with the force of 82 newtons. Since they don't give us an angle, I'm going to assume that's going directly to the right like that. It says to the left with a force of 115 newtons, so it must be longer going to the left. And I'm going to actually shorten this area up a little bit. I'm running out of room on the left side. So I want to make these kind of proportional. I know that to the right it's going 82. Let me just write that on here. Sorry, my computer's lagging just a little bit. 82 newtons right there. And then to the left we're going 115 newtons. So think of it as a tug of war when you're calculating net force here. We should see that, hey, to the left is going to be winning in this case. What else does it say? It says to the left with a force of 115, upward with a force of 565. So we have an upward force of 565, and I'm not going to have enough room to make this proportional, but I'll make it as large as I can, because it should be almost 4.5 times as big as that guy over there. And then it says downward with a force of 236 newtons. And part A says, find the net external force in the x direction. So I'm going to let to the right be positive and upwards be positive, downwards be negative, to the left be negative. So the net, and then we use this sigma symbol here to say, hey, we're talking about the net force. The net force in the x direction is going to equal to the sum of all the x directional forces. So I've got 82 newtons plus a negative 115 newtons. And so when I add those up, I'm going to get it's basically 82 plus negative 115 gives me negative 33 newtons. So what this tells me is that the force in the x direction is going to be winning to the left. That's what the negative tells me, with an amount of force of 33 newtons. Part B says find the net external force acting in the y direction. So the net external force acting in the y direction is all the forces added up in the y's. So I've got 565 newtons plus a negative 236 newtons. And that gives me a positive 329 newtons. So that's the sum of all the forces acting in the y direction. And then lastly here it says find the magnitude in the direction of the net external force on the crate. So the net external force is not F sub x or F sub y, it's just net external force like that. That's an F. I know it looks like a weird T here. Let me try writing that again. So what are the net external forces? I'm going to add up all the forces together here. I could look at this as sort of like what we've done with adding vectors before. So if I take the two vectors, I know I've got a net external force of negative 33 and then an upward net external force of 329. If I add those two forces up, I'm going to get the net external force, what I'm trying to solve for here, of this. Imagine all the forces acting on this box, or whatever it was in the beginning, is actually a crate, so it's pretty close to a box. The net external force is going leftwards and upwards, so it makes sense that our actual object here is going to be moving in that direction like that. So let's write in here our triangle sides. We know that in the x direction it's negative 33. In the y direction it's going to be positive 329. To figure out the magnitude of the red line here, we're going to use Pythagorean Theorem. So 33 squared plus 329 squared. Notice I said positive 33 squared. The negative just tells me for the diagram it's going to the left. Some students, when they put in negative 33 squared, the calculator gives a negative answer and they don't catch it. Because the calculator, to put it in the calculator, you got to put it in parentheses and say squared like that. So when I do these Pythagorean Theorem problems, I just always put in positive values and you'll get the correct answer. So adding those up, and then we're doing Pythagorean Theorem here. 329 squared plus 33 squared equals the red side squared. We'll call the red side C. So take the square root of 109,330. And when you solve for C, you should get 330.7 newtons. That's the magnitude. Now we need to know the actual direction. So 330.7 newtons, and we need at some angle. So to figure out our angle, we're going to use theta right here, and we're going to use tan inverse. So this is the opposite side, this is the adjacent side. If you take the tan inverse of 329 over 33, I get 84.3 degrees. And our answer from the book says 96 degrees counterclockwise from the positive x-axis. They're looking at it as right here. They're saying start right here, go 96 degrees that way, so you end up with like 6 degrees past the vertical, which is where we are. We could say, if we're putting a direction on this, that it's 84.3 degrees above the negative x-axis. And that would be fine. So you've seen some things like this already in the class before, so hopefully that's not too new for you. We're just applying it to forces now, a different type of vector instead of velocity. All right, look at number 3. It says a gust of wind blows an apple from a tree. As the apple falls, the force of gravity on the apple is 9.25 newtons downward, and the force of the wind on the apple is 1.05 newtons to the right. Find the magnitude and direction of the net external force on the apple. So I'm going to draw my apple. Right there's my apple. And let's draw the free body diagram on it. So we have a downward force put on by gravity, and then that's at 9 newtons downwards. And then you've got a small force right here put on by the wind. Not much force. I could probably, let's make this vector a little bit larger. So what I want to know is, what is the net external force acting on this thing? Well, all it is just adding up these two vectors. I know I have an unbalanced force going to the right and downward, so if I add these two vectors, we add them tip to tail like that, and my resultant vector is just dragging it from here to here. I want to know what is the length and direction of that vector. So the downward force is 9.25. The rightward force here is 1.05. We're going to use Pythagorean Theorem to figure out the magnitude. 9.25 squared plus 1.05 squared gives me 86.7. Square root that answer, and you get 9.3 newtons is the magnitude of the force acting on it. But now we need a direction. So I'm going to use that angle right here as theta, and I'm going to take the tan inverse of 1.05 divided by 9.25. That gives me an angle of 6.5 degrees. Now, we got to somehow word this so that whoever's looking at this knows I'm talking about this shaded angle right here. So this is, see here, the book put it as counterclockwise. They did 6.48 degrees, same thing as we did, counterclockwise from straight down, and that's fine. So you can say this is straight down, it's 6.5 degrees to the right of that. So we say to the right, counterclockwise, however you want to put it, to the right of straight down. Because counterclockwise is a better, no, I can't, strange, not strange down, straight down. All right, and that's the answer to number 3 there. Oh, I keep doing that. We're going to get to the rest of the chapter here. Number 4 says the wind exerts a force of 452 newtons north on a sailboat, while the water exerts 325 newtons west of the sailboat. Find the magnitude and direction of the net external force on the sailboat. We've done several of these in class, but remember in class we've always been talking about velocity, not so much about the forces acting on the boat. So it's pretty much the same thing. Here's our boat. We're looking at an above view. And so the wind is pushing this boat with a force of 425 newtons northward. So there's my 425 newtons northward. And then the water is exerting a force westward on the boat, so westward, of 325 newtons. They want to know the magnitude and the direction acting on this boat. So once again, I'm going to just add up these two vectors. So if I add them, I'm going to add them tip to tail like this, and I'm going to get this vector right here. Now remember, it doesn't matter if I add them this way, or if I'd have left this vector down here and added it this way. I still get that same red vector there. And that's what I want to know, is what is the magnitude and direction of that red vector. So as I put these forces in, this is going to be 325 newtons. This over here is going to be 452. Once again, use Pythagorean Theorem to figure out the magnitude of that vector. So 325 squared plus 452 squared gives me a very large number. Square root that thing, and I get an error. I typed in user error here, 309929. Gives me 556.7. So that red vector here is going to be 556.7 newtons, and now I got to put a direction on it. So I'm going to use tan inverse. This is the opposite side. This is the adjacent side. So the tan inverse of 452 divided by 325 gives me 54.3 degrees. That is this angle right here. So we have our cardinal directions on this problem, so I can say I know this is the westward direction. I'm starting in the west, I'm going north of west. So this is at 54.3 degrees north of west. So hopefully that helped you out with those 4 problems there. Let's continue on and finish the rest of the presentation. So mass is a measurement of inertia. The more mass you have, the more the object wants to maintain its state of motion. So imagine a very large football player standing on ice. To push him, there's not a whole lot of friction to push him around, but he's still going to resist you pushing him. Or if you imagine a very large semi-truck on a sheet of ice, if you go up and push it, just because there's not a whole lot of friction there doesn't mean you're going to just be able to barely touch it and the thing's going to go sliding really fast. It might be easier to move it, but it still has mass. It still is a measurement of inertia. So a very large truck sitting on ice versus a plastic solo cup sitting on ice, one's going to be easier to slide because it has less mass, and so it has less inertia. It has less of that desire to maintain its state of motion. Equilibrium is the state in motion where there's no change in a body's motion. That means the object could be sitting still, or it could mean that it's moving at a constant velocity, like you're on cruise control. You're going 20 miles per hour down the road, you're not speeding up, slowing down, or changing direction. It means that the forces are balanced. You are in equilibrium. Whatever the air resistance and friction on the road is, the car is counteracting it with the force coming from the motor. Now I want you to try page 135, numbers 1 through 3. What I'm going to do is I'm going to post an assignment link on Google Classroom. I want you to type up your answers for this. Okay? So type up your answers, submit your answers on Google Classroom. I'll read them out, or you can write them out and take a picture if you want. I think typing them, though, would probably be easier today. Maybe you can't get to a computer. So type them out, submit them through Google Classroom. Okay? Thank you, and I'll see you in class later.